So the project that you're going to be working on is called mechanism reduction. Okay. So you might, the midterm project is kind of very similar, but in terms of complexity is very, very less. Okay. In the midterm project, what you're doing is, if I basically select a species, you're just removing those reactions and you're dumping a new mechanism. Okay. So, and then you're running some 0Ds. It's not a big deal, but this one is actually mechanism reduction. And the only thing that is different here is the input interface, and that is what causes all the problems. So the problem that you're trying to solve is, if I say that I basically need my mechanism to contain a certain number of reactions. So in other words, the input is number of reactions. Okay. What is the best set of, say that I say 100 reactions. Okay. A reaction mechanism can contain 200 reactions. So the problem that I'm trying to solve is, what is the top 100 reactions that is going to give me the least error, hopefully. All right, that is the idea. That is the problem statement. And the subset of the problem is, if I say that error in my ignition delay should be, the maximum allowed error in ignition delay is 5%. What is the number of reactions? So this is the problem that you're going to try to solve for your final project. Okay. And I will give you some tips here, and in the upcoming weeks we'll be talking more about this, because I feel like this is going to be a bit confusing. So the major difference here for this particular problem is, you will first start with input conditions. So when I say input conditions, I'm talking about temperature, pressure, and equivalence ratio. Now the thing that is different here from the midterm project is, I'm giving a range for temperature and pressure. Say that my temperature is from 600 Kelvin to 1600 Kelvin. My pressure is from 1 bar to 4 bar. Again, I'm just making up these examples just to prove the point. And then finally, what I'm going to do is, I'm going to say for equivalence ratio, let us say 0.8, 1.2. So for all the question that I'm trying to answer, right? Give me the number of reactions, the top 100. Okay, I input the number of reactions. Okay, that needs to kind of satisfy all these conditions. Okay, how do I do that? That is the problem that we are trying to solve. So to start with, the way we have to do this is, now for this range of input conditions, let us say for the temperature range, I pick 10 values. Okay, 10 values between 600 and 1600, and similarly 10 values between 1 bar and 4 bar, and 10 values between 0.8 and 1.2. So in total, I have about 1000 cases. So in all those 1000 cases, so what I need to do is, I basically need to run sensitivity analysis for all these cases with respect to the temperature. Okay, we know that we run sensitivity analysis, right? So in sensitivity analysis, we are basically saying like how much a particular reaction affects the temperature. Okay, so for in this 1000 cases, you will run sensitivity. And what are you looking at? You are looking at the sensitivity of the reaction number I to the temperature. So when I say reaction number I, you have to do it for all the reactions, for all the cases with respect to temperature. So for each and every case, you are going to get a sensitivity diagram, right? So for example, for case 1, you will have reaction 1 is the most sensitive reaction. Reaction 1 affects temperature the most. You're sorting the reactions based upon the sensitivity. So for case 1, I can get some in order like this: R3, R4, R5. I'm just writing it like that. And for case number 2, I can get something like this: R2, R3, R1, R5, R6. So basically in case 2, reaction number 2 is the most important reaction, because the temperature is the most sensitive to reaction number 2. So similarly, case 3 will have some particular list, case 4 will have a particular list, and so on. So what you're basically doing is, once you get this final table, I call this as a final table, you basically sweep through all the cases. So I'm going to start with case 1. I have reaction number 1. Okay, so I basically say, I count that as, okay, I have 1 reaction now. Then I go to my case number 2. I have a different reaction, R2. So now I have 2 reactions. Say that for case number 3, R1 is the most sensitive. So you don't count it again, because that reaction has already been taken into account. So you just skip it. And in case 4, let us say R4 is the most important. All right. So similarly, first go through the first entry in all the cases. Okay, so you will have a certain number of reactions. Then you go through the second set of reactions, or the second most sensitive reactions for all the cases. And the final reaction that you have. So in a reaction mechanism where you have 1,000 species or 1,000 reactions, let us say R1000 is the last reaction. I'm assuming that this has a negative sensitivity to temperature for case number 1. Okay, so similarly for case number 2, I will have a particular order of reaction, and case number 3 I will have a particular order, and for case number 1,000 I will have a particular order of reactions. So then what you are doing is you're starting with the first reaction in all the cases. The first reaction is the most it has the highest positive sensitivity. So you start counting the reaction. So in case 1 you get R1. So let us say you have a reaction counter. Reaction underscore counter is initially set to 0. So in case 1 you take the topmost reaction. It is R1. So the counter becomes 1. In case 2 the topmost reaction is R2. So you increase the counter to 2. In case 3 the reaction is R1 again. So you don't increment it. You just go to case 4. In case 4 it's R4. So now your counter becomes 3. So let us say that basically in my first row of reactions, I only get 3 unique reactions. Everything else is getting repeated. Now I go to my second row and I repeat the process. So I count. If it is a unique reaction, I increase the counter. If it is the same reaction, or in other words, if the reaction is already included in my set of reactions, then I don't add it. So this way, I just keep looking at it and I collect the first 100 reactions that I have. So that is going to be so this is one way to describe your problem. Okay. When I say one way, this is one way that you can operate this particular code. But a more interesting way is to actually, what you call as, I basically desire an error in my ignition delay of 5%. So what is the reaction mechanism size? So given that 5% is the maximum ignition delay error that is possible, what is the reaction mechanism size? So that is what we are going to do. And to do this, again, the process is very simple. You still run the 1,000 cases. You still do the sorting of all the reactions. But then this time what you are doing is, right? Let us say that you have a reaction array. You first put the first reaction, R1. Basically from case 1, you put R1 and then you run your 0D solver. Obviously, if you have only one reaction, things are going to be bad. I mean, things are not going to run. Your Cantera may throw out some critical errors. Cantera can say that this calculation is not at all possible and it can actually exit Python because you just have one reaction, right? So let us say that you somehow overcome that, and we'll be talking about that in today's class also, which is called as, you have to catch that error. This is called as catch an exception. So sometimes in programming languages, you get an error that will lead to the termination of the program. But what you can do is you can catch those errors and you can say that, hey, if this error occurs, then just skip the calculation, right? Because in this case, it is very unrealistic to expect that you will get a decent ignition delay with just one reaction. That's not going to happen. So for the first 10 times, your program is going to crash. But it's going to most likely crash with some kind of an error saying that COD error or Cantera fatal error or something like that. We'll figure out what those error is. You catch that error and you say that, hey, if that is the error, I know that that is happening because I don't have a lot of reactions. So I need to wait till my number of reactions is sufficient so that I get a decent ignition delay. So what you basically do is you run the 0D solver and say that it crashes. What you have to do is you take your reaction array and then you add the second reaction and then you run the 0D solver again. And let us say it crashes again, okay? So you keep on adding it, and by experience, what I can tell you is if you add around 10 reactions, in total you need to have 10 reactions, then you will get an ignition delay estimate. You will get a tau IG. Obviously, this ignition delay is going to be extremely erroneous. But then now you have a target, right? You compute the error in ignition delay. And then obviously the error is going to be large. So what you do is you now include the 11th reaction. Okay, you redo the calculation. If the ignition delay is still greater than 5%, include the 12th, 13th, 14th, and so on. At some point, your ignition delay is going to drop below 5%. That is your mechanism size. So one other thing that I want all of you to do is I want you to write an input interface. What do I mean by that? Input interface. So basically, I want the input to be given in a text file. So we have a text file. So in the text file, I need to specify what is phi, what is temperature, what is pressure, what is the range of phi, temperature, and pressure, and what is the error in ignition delay. What is the error? I specify all of that, and then the calculation should be done. So this way you also learn some file parsing. You learn how to read a file, how to get the data, and how to do the calculations. So that is what this project is all about.